This is slide number 40 and I am your presenter Asloob Mudassar. Diffraction of non-monochromatic waves by a planar screen. Before we have been discussing the diffraction of monochromatic waves and we by a planar screen, and we wanted to find the field at an observation point P naught lying on the right side of the aperture. Now we want to carry out a similar analysis but with the non-monochromatic plane waves. In principle, we are going to extend our previous derivations for the monochromatic waves consisting of single wavelength or frequency, and now we want to convert that expressions that we have derived earlier into the form suitable for monochromatic waves. Here we generalized the diffraction formula of equation 63 for non-chromatic waves. The monochromatic wave quantities were U prime of P1, which represents the secondary sources in the open aperture, and U of P naught represents the field at the observation point. So you see that we had an expression for U of P naught, and we now want to convert this expression for the non-monochromatic case. So let's introduce the non-monochromatic quantities. You see that we have the monochromatic quantities over here written in capital words, capital alphabets, that is capital U prime and capital U prime at P1 and P naught respectively for the secondary sources in the aperture and for the point of observation P naught. Now the corresponding non-monochromatic quantities we are going to introduce are small u of P1 comma T, because and the point of observation, for the point of observation the non-monochromatic quantity is U of P naught comma T. So you see that you can see that we have we shall have a time dependence in these quantities corresponding to point P1 and P naught, and here you see that for the monochromatic case we had a relation between U of P naught on the left hand side, and in the integral we had U prime of P1, and similarly for these two quantities, that is for the non-monochromatic quantities, we have to express U of P naught comma T in terms of some integrals involving U of P1 comma T. So this is what we are going to do. These quantities can be connected with their monochromatic counterparts through inverse Fourier transform relationship which are given. So you see that here we are going to connect the non-monochromatic quantities lying on the left hand side of the integral, and the integral contains the corresponding monochromatic quantities. For example, in equation number 66 we have U of small u of P naught comma T is equal to the integral from minus infinity to infinity, summing up the total contributions of the monochromatic case, that is U of P naught comma nu. So we are introducing nu over here, and nu is nothing but just a variable into the e to the power iota 2 pi nu t, and the integration is with respect to nu. So you see that this expression, that is e to the power iota 2 pi nu t, is the expression that comes in the derivation for the inverse Fourier transform. So the integral and e to the and the exponential factor and the dv are the necessary parts of the inverse Fourier transform integral, and u of P naught comma nu mean that we are going to take the inverse Fourier transform of this quantity, and of course we are going to relate this one. So you see that this integral is over the variable nu, and when the nu is integrated, the nu will disappear from the right hand side of this expression, and only the time dependence will involve. So that's why we have on the left hand side U of P naught comma T, and similarly the same description for the point sources on the clear screen. So U of P1T is the point sources, non-monochromatic point sources on the aperture, in the clear aperture, and on the right hand side we have the integral which contains U of P1 comma nu, which is the monochromatic contribution of indicating the contribution of the aperture point sources at point P1. So we have equation 6 and 66 and 67, and these are the Fourier integrals through which we have connected the two quantities, that is we have connected the monochromatic quantities with the non-monochromatic quantities. Now we are going to further explain this quantity in a way. For example, same quantities but different labels. Look at the right hand side, we have u of a p naught, and on the left hand side we have u of a p naught comma nu. So these two quantities that are connected with each other. You see that when you write u of a p naught, it is understood that this quantity is being evaluated only on a single wavelength or a single frequency, and that is what we have now explicitly represented, that single frequency by the quantity on the left hand side u of a p naught comma nu. So both quantities are the same. The right hand quantities implicitly involves the frequency nu, whereas the left hand side explicitly involves the quantity nu. And similarly on the for the other equation, which is u prime of a p1 comma nu is equal to u prime of a p1. So u prime of a p1 is actually the monochromatic quantity at the position p1, that is the point source contained in the clear aperture. But you know that this quantity on the right hand side implicitly involves a single wavelength or a single frequency. We have explicitly used the frequency nu on the left hand side quantities. Both quantities are the same. The right hand side quantities implicitly involves the frequency nu, whereas the right hand side quantities explicitly involve the frequency nu. The integrals, I mean that these integrals, the integrals represent the non-monochromatic waves in terms of the continuous sum over all possible monochromatic waves. So you see that this sum, which is over the frequency nu, it means that we are summing up the contribution in equation 66, the contribution of all the points, or for all the contribution at the point p naught, summing up all the contributions due to all frequencies. And similarly in equation number 67, we are summing up the contribution at all the clear aperture points for all the possible frequencies. And you know that e to the power iota 2 pi nu t represents a monochromatic wave traveling to the left with the frequency nu, and the weighting factors u of p naught nu and u prime of p1 nu are the amplitudes of the respective wave. So you see that here in principle we are summing the waves in equation number 66, and in equation number 67 with u of p naught comma nu is the amplitude or the weighting factor for that plane wave, and similarly we have u of p1 comma nu is the amplitude or the weighting factor for the plane wave being summed up in equation number 67. To make these waves to travel towards the right, a change of a variable can be made in the above integrals from nu to nu minus nu prime, which gives. So what we have done is that we have just made a change in the frequency labeled by minus nu prime. And due to that one, when we introduce nu equal to minus nu prime, you have to change at all the other points where you had nu to be replaced by nu prime. So we have in the exponent factor we have minus iota 2 pi nu prime t, and we have d nu prime. You can calculate these values. The integrals will be also changed from plus infinity to minus infinity, but due to the negative sign which survives in the integrand, we have changed the limits back to its original values. So similarly for the equation 69 we have written them. The both expressions given earlier, that is over here, that is a 66 and 67, we have converted them, we have changed them, the frequencies from nu to nu prime. So these are the simple calculus steps. Okay, now u of p naught comma nu and u prime of p1 comma minus nu are the coherent wave disturbances. Let's find expression for them. The integral in equation 63 using a kappa p naught comma t1 from 64 can be used to write down equation number 7. So u of p naught, that is the field at point p naught, is equal to the summation over the clear aperture s1 and the integrand are u prime of p1, and there are other terms of, for example, 1 over iota lambda into e to the power iota k r01 over r01 multiplied by cos of n hat comma r01 and integrated over the surface element ds. So you see that we have explained this formula and derived this formula in equation number 63. this has implicit dependence upon the monochromatic frequency nu. So you see that apparently there are no in frequency dependence, but implicitly it depends on the single wavelength on the single frequency. For example, k is equal to 2 pi over lambda means that we are using a single wavelength. Now we want to express the wavelength k into 2 pi over 2 lambda so that we can have explicit dependence upon the frequency nu prime. So here again you know that we have introduced nu prime on the left hand side in equation number 7 to write the another equation 70. So u of p naught comma nu prime, we have introduced nu prime over here so that we can explicitly show the dependence upon the frequency nu prime, and on the right hand side we have minus iota and nu prime over v. V is the velocity of the light. So we have converted this 1 over lambda into nu prime over v, and in the integrand over the surface S1 we have u prime of p1 comma nu prime. Here we have also introduced nu prime by ourselves, and you know that in the exponent we have e to the power iota 2 pi, and we have replaced k with the nu prime over v, because k is equal to 2 pi over lambda. We have separated 2 pi and 1 over lambda was converted is converted into nu prime over v, and r01 is there as such. So in the denominator we have again r01 and the cos factor stays the same. So what we have done is that in writing the second step that we have just introduced nu prime, and we have converted k into 2 pi over lambda, and then lambda was converted into nu prime over v, where v is the velocity of the light. You can also use the c over here if you are working in vacuum. This has explicit dependence on the monochromatic frequency nu. That is the second formula in the second row. So in the third row what we have done is that we have changed the frequency from nu prime to minus nu prime only in two terms, that is on the term in the left hand side, so u of p naught comma minus nu prime, and a single term on the right hand side within the integral, that is u prime of p1 comma minus nu prime. So in the left hand side and on the right hand side what we have done is that we have made the change that we have represented the frequency nu by nu prime, so that would not change anything. Okay, so what we are going to do is that all the three integrals in equation 70 are equivalent. Using equation 70, that is the last equation, into equation number 68, the formula in 68 can be written as u of p naught comma t is equal to the integral from minus infinity to infinity, and here we have represented here we have replaced the field by its value which is given from equation number 70. That is the last step of 70 has been replaced over here, and then you know that the rest of the term e to the power minus iota 2 pi nu prime t and d nu prime are over there. So what we have, let's look at equation number 68 over here. So you see that this is 68, and what we have done is that we have written the same equation 68 now, but what we have done is that we have replaced the value of u of p naught comma minus nu prime over here, so that we can come up with an expression like this. So this is the expression that we are writing, you know, that u of p naught comma t from equation number 68, and on the right hand side we have the single integral from minus infinity to plus infinity over the variable d nu prime, and then you know that the middle term has been replaced by the term from equation number 70. That is, we have replaced u of p naught comma minus nu prime in this integral by the right hand side of the last step of integration of integral number 70. Now you know that after little bit so this is so we have rearranged the terms over here. We have the surface integral, we have taken the surface integral over S1 on the left hand side, and the integral over the variable dv prime on the right, so that we can rearrange the terms. So this is the rearrangement of the term in equation number 70, and now this becomes equation number 71. So you see that this is just only a rearrangement of the terms. The right hand side, which is u of p naught comma t, is a non-monochromatic quantity, whereas u prime of p1 comma minus nu prime in the integral is a monochromatic quantity. So we have a relationship between the non-monochromatic quantity and the monochromatic quantity. So the left hand side quantity is at the point p naught, that is the field, that is the monochromatic field, that is the non-monochromatic field at the point p naught is given by the left hand side quantity as a function of time, and on the right hand side we have the quantities which we have the field which is present in the clear aperture at the point p1 with a single frequency nu prime. To express the integrand in terms of the non-monochromatic quantity, we compute the time derivative of both sides of equation 69, which is given below. So you see that on the left hand side we have in integral number 71 in equation 71. On the left hand side we have a non-monochromatic quantity, but on the right hand side we have a monochromatic quantity. So we want to replace this monochromatic quantity with some non-monochromatic quantities at the point P1, so that we have a total relationship which is totally depending upon the monochromatic quantities. So what we are going to do is that we are going to take the time derivative of equation number 69. So here we have shown equation number 69 and we have shown the time derivative on the left of each. So on the left hand side u of p1 over t, we have operated it d over dt, and the integral has also been operated over d over dt. So in the second step we have sent d over dt, because the d over dt is a linear operator, we can send it inside the integral so that it can operate only on the time dependent part, which is only the exponent part in this case, which is e to the power minus iota 2 pi nu prime t. So you know that when this will operate on the integral, we have a rate of change of the field at the point p1 as a function of t is equal to the rate of change is equal to some quantities. You know that here again the capital quantity is present, which is u prime of p1 comma minus nu prime. So on the left hand side in equation number 72 we have a non-monochromatic quantity, whereas again on the right hand side we have a monochromatic quantity. Now what we want to do is that we are going to introduce a parameter that let's replace t by t minus r01 over v, where v is the velocity. So making these change in where the t is present. So on the left hand side we have the time derivative of u of p1 comma t minus r01 over v, and on the right hand side the rest of the quantities are the same, except that we have the time derivative taken for these quantities, and then we have replaced the time derivative by t minus r01 over v, which is changed in the exponent form, and the quantities in the integral are the time derivative that is due to the time derivative. For example, within the parenthesis minus iota 2 pi nu prime is due to the time derivative of that quantity, which we have shown in equation number 72, and replacing the time by t minus r01 over v, we have obtained the equation number 73. Now you know that this equation using equation 73 into equation 71 we obtained. So we have equation 73. So you see the look at the right hand side of the integral, that is the whole integral in equation 73. This integral can be replaced by the integral, this integral in equation 71, because the whole integral can be replaced. So replacing the whole integral over here by the quantity above, we can replace the quantity there, that is we can replace u over this quantity, which is u of p, that is the field, that is the non-monochromatic field at point p naught as a function of t. We can replace the integral on the right hand side, the singular integral over the frequency d nu prime, by the expressions given by equation number 73. So replacing that one, we get u of p naught, that is the non-monochromatic field at point p naught comma t, is equal to the double integral over the surface S1 some cos terms divided by 2 pi v into r01, and the rate of change of u of p1 comma t minus r01 over v, and the integration over the surface element ds. So this is the same integral that we have written before, that is the integral number in equation number 74. This is the same integral over here. But you know that look at this integral, it has on the left hand side it says that this gives you the field at point p naught as a function of time, and this field is non-monochromatic field, and on the right hand side you have the field at point P1 at some retarded time t minus r01 over v, and this is linked, that is the field on the on the left hand side at point P naught is linked with the field with the rate or with the time rate of change of the field present in the clear aperture at point P1. So scalar, this is the scalar diffraction formula for non-monochromatic optical disturbances. So remember that this formula is very useful. This is the formula that we can use for the non-monochromatic optical disturbances. This is based on the extension of Rayleigh-Sommerfeld diffraction formula 1. So you know that we have used Rayleigh-Sommerfeld diffraction formula 1 in order to reach this relationship. The output disturbance at the point of observation point P naught is linearly related with the time rate of change of the incident non-monochromatic waves on the aperture at the retarded time t minus r01 over v. So you know that there is a delay between the two times. The field that you will measure at point P naught at time t is related with the field present in the curvature in the clear aperture at a retarded time t minus r01 over v. In the real situation, the field at the observation point P naught is the sum of undiffracted field from the clear aperture plus the diffracted field from the edges of the aperture, irrespective of the case of monochromatic or non-monochromatic optical waves. The field diffracted from the aperture edges are actually cylindrical waves. The diffracted and the undiffracted waves superimpose to give the total field at the observation point, both in the monochromatic cases and in the non-monochromatic cases. And this is the end of slide number 40.